Today's lecture will be on an introduction to solubility and why substances dissolve and how we can tell what has precipitated out or what has been an insoluble substance. So we start with the definition of solubility. Solubility is how much or how little a substance will dissolve. There are two parts to any solution as we review. The solute is the substance being dissolved, and the solvent is the dissolving agent. In our first year high school chemistry course, our dissolving agent is almost always water. Let's go ahead and examine why certain substances dissolve. The key here is to recognize you've got an attractive force between the positively charged sodium and the negatively charged chloride ion, and there's an attractive force between the polar water molecules and either the positive or negative ion. And if it's the positive sodium ion, then the delta negative end of the water molecule, the oxygen end of the water molecule, is attracted to it. If the collective force of all those water molecules attracted to the sodium ion is greater, then the water molecules will drift away with the sodium ion, as we saw in this demonstration here. If the attractive force that the positive and negative charged ions of the solid is greater than the collective force of the water molecules, very, very little of the substance will dissolve. So we have basically three terms that we use. We have soluble. The example there would be sodium chloride in water, the example that you just saw with the demonstration. Soluble substances dissolve completely. Then you have slightly soluble, which is most of it will not dissolve. And then you have insoluble. Very, very little of the substance dissolves. You will need your reference sheet, the solubility characteristics of ionic compounds in water at 25 degrees Celsius. This reference sheet has 8 solubility rules that we follow with our class. You'll always have access to this reference sheet. It's not something that you need to memorize, but you need to be able to interpret these rules. The first sentence of each rule gives the general statement for that type of ion, compounds containing that type of ion. The second and third sentences will list the exceptions. So if you look at this reference sheet, solubility characteristics of ionic compounds in water at 25 degrees Celsius, and we look at rule number 6. Rule number 6 says most compounds containing chromates are insoluble. So that means a compound such as iron chromate, iron 3 chromate, okay, would be an insoluble compound. Very, very little of that would dissolve. Now, the second sentence of rule number 6 says the exceptions are those containing alkali metals, the ammonium ion, and magnesium chromate. So that means sodium chromate or potassium chromate would be soluble. Now, what are the factors that influence solubility? We have 3 of them. The first one, the nature of the solute and the solvent. This goes back to the attractive forces that are at work between the different substances. For example, we go back to the sodium chloride and the water demonstration that you saw just a moment ago. That was a dipole ion interaction. So you had the polar water molecule that exhibits a dipole, permanent dipole in its structure, and then you have the ionic compound sodium chloride. There's an attractive force between the polar water molecule and the positively charged sodium ion and the negatively charged chloride ion. And therefore, sodium chloride will dissolve in water. Now, sodium chloride might not dissolve as well in a substance that would be nonpolar. for example, a cyclohexane or some type of other organic molecule that wouldn't have a permanent dipole. It wouldn't have a polar, it wouldn't have a delta positive, delta negative, wouldn't be a polar molecule, and therefore sodium chloride wouldn't be able to dissolve in that substance because the attractive force between the cyclohexane molecules and the sodium ion would not be as great of an attractive force as, say, the sodium and chloride ionic compound, the positive-negative interaction that occurs within the solid. The second factor is temperature. This one we're going to examine in lab here shortly. The temperature influence on solubility. As you increase the temperature of your solution, you're adding kinetic energy into the solvent and the solute particles. Therefore, they slam into each other with a greater force, and when that occurs, there is a greater likelihood that the substance will dissolve. And so you see a direct relationship up to a point of most substances dissolving when the temperature increases. More of the substance will dissolve as the temperature increases. And we'll examine that in lab here shortly. And I want to clarify, make sure it's clear that we say most substances. It's not all substances exhibit this, but a lot do. Then finally, the third factor is pressure. Pressure influences solubility. The classic example here is your can of soda or your plastic bottle of soda. The soda company packages that soda under high pressure. When you take the cap off of your plastic bottle of soda, you hear the release of pressure. As you decrease that pressure, then you start to see the dissolved carbon dioxide gas start to release out of the solution. It's just one example of how pressure can influence solubility. Increase the pressure and you can get more carbon dioxide to dissolve into your solution of soda. So, we go back to a topic that we learned about in the fall, the ionic and net ionic equations. We've studied this process. We're now going to add an extra layer to it. For the problems that we did in the fall, I told you, or within the problem, you knew what the products were. Now, you not only can recognize and predict products from our stoichiometry unit, but now you can use the solubility rules to determine whether or not the product would be soluble or insoluble. So our first example here, we have barium chloride and silver nitrate. So we recognize that if a reaction occurs here, we're going to have a double replacement reaction. You're going to have your barium ions, your chloride ions, your silver ions, and your nitrate ions. A double replacement reaction will mean that the silver will now bond with the chlorine and the barium will now bond with the nitrate. So we write our compound with a barium being 2 positive. We're going to need 2 nitrates to balance that out. So we're going to have 2 nitrates there. Then we're going to have, for every 1 silver, we're going to combine it together with 1 chloride, +1, -1 charge there. We go back and balance this chemical equation. To do so, we're going to need a coefficient of 2 in front of the silver nitrate and a coefficient of 2 in front of the silver chloride. Now, the new part of doing this, what I just showed you was review from previous units. The new part is now using the solubility rules, the reference sheet we talked about earlier, to determine whether or not barium nitrate and silver chloride are soluble. So as I scan down my rules, rule number 3 states all compounds containing nitrate, chlorate, and perchlorate are soluble. So barium nitrate will be a soluble substance. Therefore, it's going to dissolve and produce a solution. It will be aqueous, dissolved ions in solution. Now, the second compound, silver chloride. So I look for my rule on chlorides, rule number 5. Most compounds containing chlorides, bromides, and iodides are soluble. The exceptions are those containing silver, mercury, or lead. So we have one of the exceptions. The silver chloride will actually be a solid, an insoluble compound, and therefore it will precipitate out at the bottom of our container. And that's the evidence that we have that a chemical change has occurred when we mix these 2 substances together, that we will form that white precipitate of silver chloride at the bottom of our container. All right, so that equation that we have written up on the board there with the new section of determining whether it's soluble or insoluble, this would be defined as our molecular equation. We now need to write an ionic equation. The ionic equation listed right here, separate aqueous compounds into ions. So we're going to go ahead and break apart 1, 2, and 3 substances into their ions. So we'll have Ba2 positive plus 2 chlorides, 2 silver ions, 2 nitrate ions, a barium ion, 2 nitrate ions, and the silver chloride will stay as a solid. So that would be considered our ionic equation. Then the last equation that we have to write is our net ionic equation. We're going to eliminate our spectator ions. Our spectator ions are the ones that are chemically identical. So we've got 2 nitrates and 2 nitrates, so I'm not going to rewrite that. I have a barium and a barium, so I'm not going to rewrite that. So I rewrite what's left on my equation here. So we're going to have two Cl negative, 2 Ag positive goes to 2 AgCl as a solid. And both of these are aqueous. Now this is one of those unusual situations where when you finally have this, you see that you have all 2's. So we're going to want to simplify this and write the simplest whole number ratio. So you're going to have 1 chloride, 1 silver, and that's going to produce 1 silver chloride as a solid there. And that would be your final net ionic equation. The only other problem we'd like to show you here is, based on the solubility rules in this chapter, how would you separate out mercury 2 positive ions from sodium ions? So the idea is that you have a container. This container contains the mercury 2 positive ions and the sodium ions. And what I would like to know is, what can you add to this container to get one of the substances to precipitate out rather than both of them? So only one PPT forms. So if we look at rule number 1 from the reference sheet, all alkali metals group 1A compounds are soluble. Sodium is a group 1A ion, so any compound that you attempt to form with a sodium ion is going to be soluble. Therefore, we can't add anything that'll get that sodium ion to precipitate out. What we need to focus on are the mercury ions instead. So as we scan down the list, okay, rule number 5, most compounds containing chlorides, bromides, or iodides are soluble. The exceptions are those containing silver, mercury, and lead. So we could add a chloride, a bromide, or an iodide ion, and what that would form is then we would get a compound containing, for example, if we added just the chloride, we would get Hg2Cl2 as a solid at the bottom of our container, and that would eliminate the mercury ions from our solution. There are numerous other possibilities that you could do. You could add carbonates, phosphates, sulfides. You could add sulfate. So the list goes on and on. By no means do you have to make a complete list. What you need to do is just give us one. But I want to make it clear that for each problem, there can be multiple right answers for what you could add to potentially get one to precipitate out and not the other ion.